Okay, we are still on 6.9 using substitution for integrals or use substitution. We left off here last class. Okay, so for f, I'm doing the antiderivative of the cotangent of 3x. Okay, now I'm going to show you my first guess, which is not the correct guess. Okay, if I tried to pick u equals 3x, which seems like a good guess, I would end up with the cotangent of u, which looks pretty good, but the problem is I don't know the antiderivative of cotangent u. So even though I rewrote it in terms of u, I still don't know the antiderivative and it's going to be a problem. So I'm going to pause, rewind, and then rethink this. Okay, we do not know the antiderivative of cotangent. We also don't know the antiderivative of tangent. So whenever I see an antiderivative with just tangent or just cotangent, I rewrite it as a ratio of sine and cosine or cosine and sine. So cotangent is actually the cosine of 3x over the sine of 3x. If I saw an antiderivative with tangent, I would rewrite it as tangent of u over cosine u, because we don't know the antiderivative of those quantities just by themselves, not squared or anything like that. Okay, now I look at this and this doesn't look better. It actually looks kind of worse. But I have cosine of 3x divided by sine of 3x. I'm going to pick a u. 3x didn't work, so I'm not going to pick 3x. Now, it could be cosine 3x, it could be sine of 3x. Because I'm dividing by the sine of 3x, I'm going to pick sine of 3x as my u value because I'm dividing by it. So at least I'm doing something to it. So it's a composite of something. There are other ways to do this. And if you watch the algebras, they did it a slightly different way. Get the same answer. Okay, now I'm going to try this and then see if this is going to work out. Okay, du equals the cosine of 3x, chain rule times 3, and I have to remember to put my dx here. Okay, when I rewrite this, I have picked u to be my denominator. I'm left with a cosine 3x and a dx. So I'm going to solve for dx, and I'm going to multiply by the cosine of 3x. Okay, so dx equals du divided by 3 cosine of 3x, right? Okay, so I have the thing I have left is I have the dx, which is this expression, and I'm timesing it by the cosine of 3x. Okay, this is scratch work, so I'm going to go ahead and do it at the same time. Some of you will do this in your head. The cosine of 3x are going to cancel, which is good because I don't want any x's left in my expression. So where dx is, cosine 3x and dx, I'm going to make it du, and I still need a 3 at the bottom. Again, du normally goes on the right side. I do need a 3 at the bottom. Since it's awkward, I'm going to put it over here. You could put it next to the u. That's equally fine. Okay, now I now have an expression in terms of u, but the question is, do I know the antiderivative of 1 over u? And I do. It's natural log of the absolute value of u plus a constant. And I'm going to go ahead and plug my u value back in. Plus c. If you check your answer, it should give you, by taking the derivative, it should give you this is the answer. Again, there's other ways to do it. You should get the same answer both ways. Okay, now for G, this one's an interesting one that often comes up on the AP test. So I'm showing you just in case you get that one question on the AP test that looks like that, and you're like, what should I do? Okay, it doesn't look that bad though. It's the integral of x divided by the square root of x plus 1. Since I'm square rooting the x plus 1, it feels like u should be the x plus 1. Okay, du equals dx, which is like the best type of du. Okay, so at the bottom, I'm going to have the square root of u. Now dx is the same as du, so this is automatically going to turn to du, but I have this weird extra x at the top, and it's not going to cancel because there's no x here. Okay, so I'm going to have to think about what to do here. I am going to make this du. Okay, now where the x is, I have to replace it with something. Because I wrote that u equals x plus 1, I'm going to rewrite this as x equals. If I solve for x, I would minus the 1, I would get x equals u minus 1. So in this weird one situation, because I have this random x up here, and because it's easier for me to solve, it's easy for me to solve for x in my u expression, I'm going to make a substitution. Okay, now looking at this does not look great. Still looks like some kind of quotient. But because the denominator is just u to the 1/2, I can actually simplify this, and then I can find the antiderivative. I might not want to, but I can do it if I had to. Okay, this is, I'm gonna write it on the side. This is u to the 1 over u to the 1/2 minus 1 over u to the 1/2. If I split it up, if I do 1 minus 1/2, I get u to the 1/2. If I do, on the other one, if I have 1 over u to the 1/2, that's u to the negative 1/2 du. I can do the antiderivative of this. That's going to be, oh, wait, don't write antiderivative because I took the antiderivative. Let me raise it to the 3/2, divide by 3/2 or multiply by 2/3. And then I'm going to raise this to the positive 1/2 and then times by 2. And I'm going to remember my constant. Okay, and then I'm going to go ahead and plug my u back in. U is x plus 1 to the 3/2 minus 2 x plus 1 to the 1/2, or you could write square root of x plus 1 plus c. Okay, and then I went ahead and I got the antiderivative. Okay, this strategy, it doesn't happen often, but it happens occasionally. So if you get stuck on one, think, oh, maybe I could solve that extra variable in terms of u, and then I can make it work. Okay, now h is another type of u substitution that comes up, and you're going to know when it happens because it's just not going to quite work out. Okay, so now if I were doing it like before, I would pick u to be probably the part on the bottom, the part in the radical, the 1 minus 4x squared. Okay, it's not right, so don't copy this. Okay, and then I would do du equals negative 8x dx, and I would solve for dx, and I would get du over negative 8x. And then I have the dx and I have a 1 here, but normally I have some kind of x, so the x's are going to cancel, but the x's aren't canceling. So now I have a problem and I didn't pick the right u. Okay, if you have a weird fraction, you should think this could be the antiderivative of some kind of inverse trig, or the derivative of an inverse trig. Okay, the ones we most commonly see, because this has a square root, I'm thinking this is this, which would look like arcsine. Okay, the other one we see a lot is arctangent, which would be something like this. So I'm kind of trying to think of what the answer is before I start. If it were arcsecant, it would have the weird absolute value and I would kind of give it away. Okay, so this looks more like this one. So I'm thinking I'm going to try to make it look like this. If I want it to look like 1 minus u squared, I need to think about what I squared to get 4x squared. Okay, in order to get 4x squared, my u would actually have to be 2x. And let me rewrite this so we can see how this would work. 1 over, and then in the square root, I would have 1 minus, if I do the quantity of 2x squared, I do get 4x squared. So this would be my u right here. Okay, now I can't leave dx here, so let me solve for the derivative. Du equals 2 dx. Let me solve, divide by 2, I get dx. Okay, so for dx, I want to replace it with du, and it's over 2, so I need to put a 2 at the bottom, or I put a 1/2 in the front sometimes if I don't have room. Okay, so now it is written in terms of u. I know the antiderivative of that expression is arcsine of u, or inverse sine plus constant, and I can just put my 2x back in. Okay, so if you see a fraction, and there isn't really anything interesting in the numerator, just think this could be arcsine, it could be arctangent, whichever one looks more convenient, you're going to try it that way. Okay, last topic using substitution is definite integrals. Okay, the main thing with the definite integral is you do need to change the boundaries when you change variables. Okay, we'll show you when we get there. We'll start off just figuring out the u, although hopefully we're getting good at it. Okay, this is the antiderivative from 0 to 2 of t squared times the square root of t cubed plus 1. No product rule for antiderivatives. Since I'm square rooting the t cubed plus 1, I think u is going to be t cubed plus 1. Derivative is 3t squared dt. And because I know I'm going to need the dt, let me go ahead and solve for dt. Okay, now I'm going to rewrite it. I'm not going to put the numbers on it yet because I know that they are messed up. Okay, I am left with a t squared and a dt. This is my dt. I need to times it by a t squared, which is great because now the t squareds cancel. I'm left with du, and it's over 3. I'm going to go ahead and put the 1/3 over here for no reason other than it's out of the way. Okay, it looks good so far. Now here is the issue with the definite integral. It's not an issue exactly, it's just an adjustment. The integral started with 0 and 2, but this is representing t equals 0 and t equals 2. Now that I have rewritten this in terms of u, I need to know what u equals to and what u equals to. The boundaries are going to change. Okay, now to figure out what u equals to, I need to see what expressions for u. U is t cubed plus 1. Okay, so I need to plug my t value into u to see what I'm going to get. You don't need to show words. You could do it in your head. I'm going to do it here though. U equals, so the first t value I got was 2. If I plug that in, I get 2 cubed plus 1, which is 8 plus 1, 9. So the upper boundary is going to be 9. Okay, on the bottom value, the t value was 0. If I plug that in here, 0 cubed plus 1, the u value is going to be 1. So this is the integral from 1 to 9 of 1/3 square root of u du. You have to change the boundaries or it's no longer true. This is equivalent to this, but if you don't change the numbers, it's not. Okay, let me take the antiderivative. What is that? U to the 3/2 times 2/3. I don't need to put plus c because this is going to go from 1 to 9. Okay, let me simplify this a little bit. This is 2/9 u to the 3/2 from 1 to 9. Okay, now that I've changed it to u, I don't have to go back to t. I'm just going to plug in right now. Okay, so 9 to the 3/2 minus 2/9, 1 to the 3/2. Okay, 9 to the 3/2. The bottom number is the square root. So square root of 9 is 3. 3 to the third is 27. 1 to the 3/2 is 1, which is great. So I have 54/9 minus 2/9, which is 52/9. That's my final answer. Okay, let's try one more definite integral with substitution now that we've seen the process. Okay, last one. Integral from 0 to pi over 2 of cosine x times the square root of sine x. Got weird product going. Since I'm square rooting sine, I'm going to let u equal sine x. Derivative is cosine x dx. I know I'm going to end up thinking at least about what dx is, so I'm going to go ahead and solve it. Let me go back to here. I am square rooting u. Great. Okay, now besides the square root of u, I still have a cosine x and a dx. Dx equals this. And then if I were to times by cosine x, the cosine x's cancel, and I'm just left with du, which is lovely. Okay, now I'm not going to write 0 and pi over 2 here because those represent the x values. I want the u values. Okay, so to get what u is, I'm going to plug this in to the u equation. The sine of pi over 2 is 1. This is 1. The sine of 0 is 0. So now my integral goes from 0 to 1, which I like better than the original anyways. Now let me take the antiderivative. 1/2, that's 3/2 times 2/3 from 0 to 1, and I can plug in right here. 2/3 times 1 is 2/3 minus 0, and I get 2/3.